he should tell you. I know he does quantum dots and things like
Ah,
that.
okay, okay, yes. Oh, then I think I know. For I did not understand because no, then I don't know. I know another guy who's here.
You know.
So buy my thank you. Okay, so now we'll go to the third seminar. So it's a pleasure to have Rosario Fazio from ICTP. So of course he's also a member of our scientific council. So
Thank you.
Present his.
Okay, so thank you very much, Nathan. I will talk about yet another different type of crystals. These are also kind of exotic state of matter. I will try, so in my talk, to give a flavor of the topic and a little bit of tell you what's going on. And if I have time, I will also tell you what we are doing in this field. But before talking about time crystals, I really would like to say a few words about quantum simulators, because they have a key role in this topic, as the idea of quantum simulator was really crucial in observing time crystals in a lab. So what are quantum simulators? So this is an old idea. So it started from Feynman. And the main motivation, and actually this was the motivation why people really started to pick up this Feynman's suggestion in the last, I don't know, 10, 20 years, was that in addition to analytical and numerical tools, there were problems in quantum many-body systems which were quite tough to be studied. And so, following Feynman's idea, people developed a way to study quantum system by means of other quantum systems which are controlled in the sense that, at least in principle, experimentalists know how to change knobs and implement the model they want to do. So for instance, I think the main motivation was, for instance, in high temperature superconductivity or complex frustrated quantum magnets, there are models which are believed, for instance, to capture the main properties of high temperature superconductivity, the Hubbard model. However, the Hubbard model is pretty tough to be solved if you go beyond the perturbation region. And it's pretty tough both because analytics is complicated, but also because of numerics. Numerics is difficult. And part of the difficulties is related to sign problems. If you do Monte Carlo, it's related to the exponentially large Hilbert space. If you do exact diagonalization or other methods, all these problems disappear if you have a quantum system which is not used, which is just used as a simulator. However, even this was, if this was the main motivation, I really would like to stress another aspect which will become very important in this talk. That is, not only quantum simulators are able to study complex model Hamiltonian. In addition, actually, in the last years, there were also instrumental to study certain questions like thermalization or the absence of thermalization, these type of things which in the real system are pretty difficult to approach, but also, and this is the topic of my talk today, actually they are able to simulate state of matter which in principle they may be allowed by the laws of nature that however are essentially impossible to find spontaneously because they are so fragile that any type of imperfection, noise will forbid their observation. And so I will come back to this point when I will talk about time crystals. So by now, I mean, the field exploded because there are many experimental platforms going for trapped ions, optical lattices, and in the framework of this talk, essentially the experiments were done with ions and with trapped ions and with Rydberg system. So this is a small closing the intro to quantum simulator. So to start with the time crystal, let me motivate the question. So the topic is pretty recent. I think the first paper by Wilczek is from 2013. So it is about spontaneous symmetry breaking, and this is just a canonical example, a textbook example in which by changing, so this is an example of a quantum system, by changing a certain parameter, then below or above whatever critical value, then some order parameter becomes different from 0, which signals the fact that the ground state in this case breaks spontaneously the symmetry contained in this Hamiltonian. And there are, I mean, a lot of very important features associated to the properties of universality, or to all the properties that has the system close to the transition point. So depending on the type of symmetry that is spontaneously broken, then you will have certain order parameter which will capture this, this transition to this ordered state. Now, Wilczek in so 2012, just in this paper, tried to address the question if time translational symmetry can be spontaneously broken. So this question was related to the fact that if this is the case, then analogously to crystals where you just break translational symmetry, then you will have a certain kind of ordering in time. I will tell in a moment what people think about it. And he just named this situation the realization of a time crystal. So there are several questions which arose already after Wilczek paper. In part, they were already discussed in this initial paper. So first of all, I mean, it was not even clear if the laws of nature will allow the existence of these time crystals. If yes, then it is the next question was to understand how to characterize, and you will see, I will tell you in a moment, that in the first couple of years this was not even completely clear. Next, where to look for it, and this was the point where quantum simulators became essentials. So far, There are several experiments, but essentially the most convincing one are just in controlled artificial systems, synthetic systems. So there are no, yes?
Was Wilczek's question a theoretical question or an experimental question? I didn't understand.
So in the first paper, I think Wilczek studied, okay, so why people found all possible symmetry broken phase and time translation is not broken. This was his initial question.
Theoretically, it's possible, right? Or
So I think the way he put, he was not even sure that this was possible. No, it is possible, but he did not know if this could be found in any place.
in nature.
In nature, yes. He just put it in a kind of more dramatic way, saying it's the laws of nature, but it's possible, yes. Yeah, so these were, so let's say the initial parts, once people realize that, I mean, actually time crystals exist, actually you find out that maybe there are certain features of time crystal that are not so exotic, and actually you may connect.
Curiosity. I still don't understand what time crystal is.
No, because I did not say it.
So how do you answer question 1 without answering question 2? Don't you have to answer question 2 before 1?
Yeah, question 2 should be before question 1.
Not really, because I will tell you why. But I'm happy if you want to put first question 2.
How can you answer the first question if you do not define what's a time crystal?
So a time crystal is a state of matter where time translation invariant is broken. Now, the next question, no, for me it's the next question, but I'm happy, just a sec.
This is the first question?
This is my first question.
So this is the answer to your second question?
No, because I still have to give you what is the order parameter.
Okay, go ahead.
So, okay? But I would not insist on this, okay? Good. And you may ask, okay, what can we do with something? But this, I mean, I don't think I have time to say anything about this. So more or less, the presentation of the outline of my talk is, I will give a quite long introduction to the history. I mean, which is, even though it's just only a few years, there were few steps every year, which are, I think, worthwhile to comment. And in the second part, I will say more about some features about time crystals where we were involved. And if I manage, but I'm not that sure, I would like to say something about possible connection to synchronization. And before I forget, I should say that I really would like to acknowledge collaboration with many people, which I will not list, but say in all these years I had fruitful collaboration on this topic with many people. Now, then probably this comes, so I think after after Wilczek's paper, essentially people trying to find an order parameter. And the first few papers were pretty, there was a kind of confusion. So there were proposals, it was clear that they were not time crystals. And if I can say part of the confusion arose because, I mean, you might be tempted, I mean, of course, it's trivial what I'm going to say, but you might be tempted to say, okay, you just break time translation invariance if you have certain observables which oscillate in time. But this is clearly wrong, because in quantum mechanics, any two-level system, you have Rabi oscillation, so this does not work. And let's say, just to give you an historical, so for 2 or 3 years, so there was a paper publishing a suggestion for a time crystal and another paper showing that this could not be. So I think one key contribution to this, all this discussion came in a paper by, so in 2015 by Watanabe and Oshikawa that just generalized to time-dependent situations, say standard off-diagonal longer range order. So you just take just a local order parameter phi. This can be magnetization or whatever. And you just take correlation function, you go to the thermodynamic limit, and so here there is, I mean, does not need, it can be t and t prime. And if you send the 2 points x and x prime to infinity, then you, instead of getting something which is constant, you should get something which is time dependent. And, but the most important, so I would say this is kind of natural way to define a time crystal. What was very important was that in this paper, they were able to prove that if you have a system in thermal equilibrium, or you have a system, say, in the ground state, so they could prove it for short-range interaction, then time crystals cannot exist. Now, this is very important because, so first of all, this paper ruled out all possible situations where to look for time crystals, but also, I think, made clear that somehow the analogy, the natural analogy with space crystals, ordinary crystals, could not be pushed further. While space crystals are equilibrium, I mean, state, thermodynamic equilibrium states, then if you want to look for a time crystal, then the only possibility is to look out of equilibrium situation. So the first, and so far the most successful examples of a time crystal were looked and realized in quantum systems which are periodically driven. So quantum systems which are, they have a unitary evolution where, however, the Hamiltonian is, has some periodic time dependence. So the first two groups who had developed this idea of what are called Floquet time crystals are, so this Else, Bauer, and Nayak, and the group of Sondi in Princeton. So this happened in 2016, soon after there were two experimental work, just realizing exactly the theoretical proposal. So there are some kind of well-defined and more formal definition of time crystal in terms of the Floquet spectrum of the unitary evolution. I will try to be, so I will be sloppy and just give you the rough idea. Now here, so since you have an Hamiltonian which has a period t, I mean, you will have a spontaneous breaking of time translation which is discrete. So essentially, one should observe that certain observables will have an oscillation period which is a multiple of this. So if you want, yes?
I mean, if you have a Hamiltonian depending on time, why is it spontaneous? It's kind of explicit.
Right. So, but so this is what you break is that. So for instance, if you have a lattice, sometimes you may have a situation in which you have a charge density wave. So the state doubles the periodicity of the lattice Hamiltonian. So you just break discrete symmetry.
Sure, but I mean, spontaneous breaking, at least in quantum field theory, means that the Hamiltonian has the symmetry, but the vacuum state doesn't. You see what I mean? Right. Here you have the Hamiltonian not having the symmetry.
So I think that what you are breaking is not a continuous symmetry, but a discrete symmetry. I think, yeah, so I can make examples. So I'm a condensed matter, so, but I think it's charge density wave, spin density wave is a good example of a state which has not the same symmetry of the Hamiltonian.
If energy is time dependent, then what is the definition of the vacuum?
No, but there is no, so you reach a steady state. I will come to this point. So this is a key point. I will come to this. But this, we are outside equilibrium, okay? So if I can say in different language, essentially in this case, you have a many-body system in which you develop a kind of period doubling or period multiplying, which will appear only in the thermodynamic limit. Okay? So as I said, you can give a more formal definition by just looking at the Floquet spectrum and just look at, so essentially, the Floquet spectrum should have a certain multiplet structure with the corresponding eigenstate violating cluster properties. So I will give you some trivial example that you will not like, but I hope to go through and just show you that there are non-trivial examples. So let me start with some very stupid case that, but I think it helps because it is related to actually the experimental realization. So a very simple evolution, periodic evolution that you can have, you just take a spin 1/2 Ising. Why this order? It's important. And then after a while, you just do a spin flip. Then you let evolve the system, flip, let evolve the system, so on. Okay? So the evolution of the system is just composed by just evolution plus the flip. So the question is that looking at the evolution and magnetization. Now, as I said, this is very trivial example. So if you see that the Hamiltonian has a period t, if you look at the state, this is just an example, then you will see that the state will have a period which is 2t, okay? Because if you start with this state, then you will go back to the initial situation only after 2 periods. I mean, as I said, this is a trivial example because there is no many body physics involved. I mean, no thermodynamic limit. However, you can show that in this case, the system is fragile to any arbitrary small perturbation. Okay, so you just take epsilon small perturbation, then this period doubling will disappear sooner or later. It is the many-body features that make the system stable. And actually, I mean, as I said, you may look at the the properties of the correlation of the, the properties of the Floquet eigenstate, but essentially, just to give you an idea, in order to define a Floquet time crystal, so first of all, I mean, you should not have any fine-tuned Hamiltonian to realize this, or any fine-tuned initial state. You should look for a phase, not just singular cases that can be constructed and have nothing to do with, I mean, they can survive also outside the thermodynamic limit. If you implement this, however, and this I come, I think, probably to your observation. So if you take a unitary system and you just drive it periodically, then generically, if the system tends to thermalize, it will thermalize to infinite temperature. So locally, it will look like an infinite temperature system because you are absorbing energy. And so it is not expected, actually, you can rule out any type of ordering in time. In order to observe a time crystalline phase, somehow you should be able to consider a system in which the dynamics breaks ergodicity. Okay, so you should find situation in which this occurs. This is not guaranteed that the system will show time crystalline phase, but at least it's a kind of requirement. Now, the first suggestion by the two groups was to consider a disordered spin system where you have many body localization. So if you have a system in which many body localization takes place, this is also a system which is unable to absorb energy. So due to the interplay between disorder and interaction, the system is not able to absorb energy, and so you have the hope to see a non-trivial behavior. So this is an example which was given in this initial paper, in which essentially what they measure by just numerical simulations, they just measure correlation function in time. So essentially this parameter Z is kind of just measure the fact that you have period doubling, okay? So the system will reach, despite being unitary, will reach a kind of stationary state, which at any finite system will be the case in which the system has no ordering in time. So if you have perfect period doubling, then this Z should be 1. However, any finite system has no period doubling. But what is interesting, I mean, I just took their results, but this was later confirmed in several papers, is that you see that, however, when you can do some kind of finite size scaling, and then you see that, as should be expected, the time at which the period doubling disappears diverge. In this case, diverge exponentially with the system size. I mean, here systems are small, but you really see that this divergence will, or this persistence, sorry, of period doubling will only emerge and be stable in the thermodynamic limit. Now, being stable means that you may deviate, you change the parameter of the Hamiltonian, you change the initial state. Somehow, this is a robust feature of a certain phase in the parameter region. Now, many body localized states where, and this exactly this type of pulse sequence was realized in these two papers, in the group of Monroe in Maryland and in group of Looking in Harvard. They just exactly did this type of simulation. So just forget about all the details, but essentially they analyze the spectrum of the oscillations in the magnetization, and essentially they just were seeking for a component at half of the frequency, which would tell you that in that case you had period doubling. So this is one example, and you see that in the absence of interactions and disorder, then this component will disappear. I mean, it can only be there only for fine-tuned case, which, however, are essentially impossible to realize. It only appears as a many-body phenomenon when interactions are turned on. So these were the first two experiments. Now, frankly speaking, I don't remember if this figure belongs to this paper or to this paper, sorry. But since then, there were a few other experiments in NMR and this type of systems. So I will skip the discussion about stability, because I would like to tell you a little bit of a few other examples where you can look for time crystals. But so what I'm going to talk next in the last, say, 15 minutes, 15 minutes, right? I started at 12, 12 right? It's about some other, issues that people and we start discussing. So, as I said, MBL was, and disorder was a key, a very good example to have a dynamics, which a non-ergodic dynamics. And it was great because experiments could be done. But in principle, the question is that if you want to, the question is disorder crucial, or you may find other examples in which the dynamics is non-ergodic. And so you may have time crystals. All the examples that were realized in, so far, experimentally, only have period doublings, because all the systems which were studied were spin one-half system. But of course, you can go and have more complex situation in which you have spin S, and this will imply that in principle you may have higher ordering of, I don't know, say period tripling and so on and so forth. And in principle, you may have, these are, you may have also transition between different types of crystalline behavior. But I should say that these are, at the moment, just theoretical discussions, so there are no examples. The easiest system from theoretical point of view, where you can see this, so time crystalline phases in the absence of disorder, are infinite range models. In particular, the LMG, Lipkin-Meshkov-Glick model, which is just a very simple infinite range spin system in a transverse field. Now, this is an exactly solvable model. It's simple, which has a nice property, which is crucial in this context. That is, the system has a finite range in the spectrum below which, so energy range, below which all the states are all the eigenstates has ordering, spin ordering. And so this is something I did not say, but is important. So far, nearly all the example, I would say, of time crystals that were studied were kind of system in which there was a kind of hidden ordering in addition to the time ordering. So the result, so sorry, the analogy or the calculation go exactly along what I told you before. So you just do the same pulse sequencing trick. Here, the ergodicity breaking comes from the special type of dynamics of this model. It has nothing to do with, with disorder. But then you really see the same type of period doubling in the magnetization that if you analyze in more details in its Fourier spectrum, you see that there is a small gap here which signals that any finite system has no time crystalline behavior, but this gap closes actually also in this case exponentially with the system size. You may also go a bit further and just look for more complex models. So what we study, I will not say much about this, but I would like to discuss in 10 minutes dissipation. So you can go and consider also more complex systems, so these clock models, which are essentially generalization of Ising models, so n-state clock models. And so the two or three special features which probably I would like to emphasize here are, so first of all, you can get time crystal with multiple periodicity, so period tripling, fourtupling, so on and so forth, which I would say is not that special. Something else which we found interesting is that for some reasons, well, I can tell you more if you're interested, but for some reasons there is a connection. So these models can be mapped in parafermion models. And so essentially, you can see that the time crystal phase is related to the model being has certain properties related to the corresponding phase in the parafermion language. This is just just a case, or there is something deep, frankly speaking, we still do not understand. So the last 10 minutes, I really would like to discuss so this aspect, which so personally I find it interesting. So trying to understand if the bus, so environmental issues are important, detrimental or not for time crystals. In many protocols in quantum information processing, and in all these examples I gave you so far, it was crucial to have a nice unitary evolution just to keep alive all this subtle interference which leads to period doubling. But actually, this is not the only option that we have. There may be cases in which actually the environment itself is crucial to induce a time crystal in this case. So it's a continuous time crystal. So the Hamiltonian, so both the Hamiltonian and the coupling to the bus is time independent, yet the system develops a kind of many-body limit cycle, which effectively in the steady state shows a time symmetry breaking. Now, if you approach the system, there are two aspects which are important. So first of all, since you are considering a generic system coupled to non-equilibrium bus, so the no-go theorem does not apply. There is an interpretation that I'll just very briefly tell you in a sec, in which you can just connect also this to the previous case, but then here you can see that the ordering does not occur in the bulk, but it's a kind of boundary phenomenon. The last thing I would like to tell you is that actually in this picture of dissipative quantum many-body dynamics, then you get into a description which is very close to what people studied in synchronization. And so people are starting seeing that there are good connection between these two phenomena. So just let me give you, so the bad part that I will not discuss because of lack of time is the fact that so far the only examples that people, so that we found are examples which are hard to realize experimentally, and so many results are a bit out of control for reasons that I will tell you in a second. So just imagine that you have an Hamiltonian system which is composed, but you can imagine just for visual simplicity in terms of a boundary. These are these orange dots, a bulk, and some interaction. Now, the whole system is just evolving through a unitary evolution, Schrödinger equation. But say that you are interested in the boundary alone. So the only thing you have to do is just to trace out the blue dots. And what you end up is just a dynamics of the reduced density matrix through some, some equation. So for instance, if the system is Markovian, but it's just an assumption, I'm not saying anything about it. So we know that this L should have a Lindblad form. But now the point that I would like to stress here is that if you just look at the reduced system, so this is a kind of many-body open system, but then having a kind of breaking of time translational invariant only on this surface means that this equation should develop a kind of limit cycle in the steady state. So the simplest model, which is nice because you can work it out easily, and so you know what you are, so you can control. It's a very stupid model, but still not. So it has non-trivial dynamics in which you have a collection of spins that are interacting through some collective damping to an environment. So in principle, you can reconstruct this reduced dynamics by some boundary plus bulk, but I will not go in any details. I mean, this model, because of the collective coupling to the bath, has a phase diagram which has two phases. So this was worked out recently. So the two phases are the one in which the magnetization along sigma z, along z is different from 0 or not, depending on the relation between the splitting and the damping constant. Now, what is interesting is that just to look at the spectrum of the Lindbladian, which is different in the two phases. I mean, I will cut short. Essentially, it's gapped in one phase, it becomes gapless. Now, this fact of being gapless results in the fact that if you look in the gapless phase at magnetization, then you will see that the magnetization will have oscillation which are damped. But the interesting point is that they will enter a limit cycle when you go to the thermodynamic limit. So in this way, you can talk about this many-body limit cycle as a kind of continuous time crystal. Here you don't have period doubling, but it's just the time spacing of a time crystal is fixed by the various parameters entering in the dynamics. Now, there is an interesting part into it, that is the fact that there are many systems, controlled systems, say many-body open systems, which are being realized using circuit QED or optomechanical arrays. which in principle may show this kind of many-body limit cycle. And would be interesting to see if this is the case. Unfortunately, experimentally, it was not observed. The theoretically calculations so far were essentially all variants of mean field calculation, and this level is not clear if mean field is an accurate way to study the dynamics of the system. What is interesting, however, is that this system have a very nice connection to, if you like, to synchronized motion like Kuramoto-like models in the classical dynamics, so that you start seeing that this time crystalline phases may be yet in some form a manifestation of a synchronized motion. So, yeah, so for instance, there are cases in which... No, thermodynamic is n going to infinity.
I'm sorry, but so what I want to know is, when you talk about synchronization, who synchronizes with whom? I mean, you just said that it would be like a Kuramoto type. In the Kuramoto, you get the oscillators synchronized. Here, who synchronizes?
Yes.
Each of the crystal with the others?
So, yes. So the closest to Kuramoto-like here are a system in which you have boson-like fields which are defined on a lattice, and what they synchronize are the phases of this.
Okay.
Okay? So it's kind of...
Okay.
Okay? So I think I do not repeat the conclusion, and I thank you for the attention. Thank you.
Just to, I mean, the quantum thing about the examples you gave is the magnetization, the fact that you have spin and you have magnetic dynamics. Are there examples of time crystals where you have
Yes.
both quantum dynamics and classical?
So there are,
classical limit?
yes. So there are only very few examples of classical studies. I don't know why. So I can tell you, for instance, what we studied was a Kick model of Kick's Hamiltonian model, many body models of rotors. And there you can see that you may have features like that. But, I mean, there are just two examples. It's not, I mean, yeah.
So sorry, I'm not in the area, but I'm a little bit confused, because as far as I knew, these time crystals were related with systems associated with Hamiltonians, which were time independent, but the solutions were time dependent because of spontaneous symmetry breaking. And as far, I may be wrong, but as far as I would like you to comment further, as far as I know, the prototype example given by Wilczek himself was of a constant potential, electric potential in a Josephson junction, which develops because of a spontaneous symmetry breaking, a oscillating current, and so the solution would be time periodic. So it would have a independent, a Hamiltonian, which is time independent, developing a time-dependent, time-oscillating solution because of spontaneous symmetry breaking.
Yes.
So is that a definition of a time crystal? Is that an old-fashioned definition? So could you elaborate a little bit?
So you are right in all what you said. Let me say that a time crystal is a state, is a situation in which the state does not respect the symmetry of the Hamiltonian. So if the Hamiltonian is time independent, this is exactly what you said. But you may have cases in which the Hamiltonian is periodic, and then the system should break this natural periodicity, which would be period doubling. The original suggestion of Wilczek was essentially to say that the AC Josephson effect is an example of time crystal, meaning that you apply a bias voltage, and then the system will oscillate at a given frequency, which is the Josephson frequency. Now, this is a controversial, so not everybody is convinced that this might be a situation. However, this goes more into the last part of my presentation, where in order to keep a voltage bias, then you need to couple to an environment. This is not a closed system. So it may be closed if you look only at the superconductors, but in order to keep the difference, then you have to connect at the reservoir. So this is more like an open system which sustains a periodic motion. I would be inclined to believe that this is time crystal, but I should say it's not completely accepted. I mean, other examples, for instance, I think if you talk to the optical lattice, of the quantum optics community, they will tell you, look, a laser is it may be also. Actually, yeah.
So can we define then a time crystal as a system whose solutions have different symmetries
Yes.
than the Hamiltonian?
Yes.
Time symmetries than the
Yes.
Hamiltonian?
Yes.
Okay.
And sorry, just to my remarks, there is a very close and nice connection between lasers, dynamics, and the AC Josephson effect, which was studied, I think, in the past.
Any other questions? Okay, so let's thank Rosario again.
Thank you.
So we start again at 2:15.
Have a good day. Nice to see you.